start. Okay, all right, so let's keep going. I'm not sure if Gordon's gonna call back in or not. Okay, so this part makes sense. I was kind of drop off when I was trying to say, you can think of this long multiplication form similar to this one. It really is, because this is just a very, it's a very special case of a polynomial. You know, you can think of it both ways. In reality, really, this is like, you know, a base 10 polynomial per se. That's why you can do it this way. They're the same thing. We're like I said, we start with studying special cases, and then we study the general case, and the generalized case are kind of connected to the specialized case. Anyhow, so this question is, must the product of two polynomials always be a polynomial? It's similar to must the addition of the two polynomial be same as is also polynomial? The answer is yes. Okay, so similar to when you add two polynomial, you always end up with a polynomial. When you multiply two polynomial, you'll always end up with another polynomial, right? And think of it, as you multiply them, you are adding more terms. And none of these A and B's are 0, so you are going to end up with some form of a polynomial. Even if they cannot cancel each other out, you will still have the constant term. Even if you multiply 2, you end up somehow with a 0, which is not likely to happen. Yeah, you can multiply the 2, end up with a 0, except when 1 is 0. But in that case, you always end up with a polynomial. Okay, so there's no way for this to not be a polynomial. So the answer is yes, the product of two polynomial will always be a polynomial. So that's a pretty trivial question. So let's investigate more. Yes. Okay. So 18.6. Suppose f of x and g of x. I'm assuming that you're familiar or you're comfortable with the notation of f of x, g of x by now. If not, you just think of it, it's just a functional form. Suppose there are non-zero polynomials, okay, which is important because, like I said earlier, you can only end up with a 0 polynomial when you have multiplied that by a 0 polynomial. So h of x equals to g of x multiplied by f of x multiplied by g of x. Okay, how is degree of h related to the degree of f and g? Okay, so that's just some conceptually checking. So suppose we say f of x equals to an xn plus an minus 1 xn minus 1 plus an minus 2 xn minus 2 plus dot 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 plus a1 x1 plus a0, and g of x equals to b m. We use m to distinguish the power. M doesn't have to be the same as m, although it can, but it's just another constant term. Minus 1 plus b m minus 2 x m minus 2 plus b1 x1 plus b0. Okay, so these are two. M doesn't have to, m and n are two non-negative constants. Okay. Think of the long multiplication form we had earlier, right? The degree of f of x equals to n, degree of g of x equals to m, meaning the highest term. Okay, all right, so one question is, what if it doesn't have every single term, it skips term, right? So like what we had earlier, you have x cubed, and then the next term is x, there's no x squared. In that case, this constant or this coefficient is just 0 to remove that term. So you can always write it in this form, even if not every single term is present in the function. You can always write it in general in this form. Maybe that's trivial, doesn't need to be mentioned, but all of this, an can be 0 and bm can be 0. Okay, every other term can be 0, but if the degree of f of x is n, then an cannot be 0. So you cannot have a 0 coefficient here. If you do, then it's reduced down to the next degree, right? So these are just the conditions. All you need to know is the first term is not 0. All the rest can be 0 for this to be a n degree polynomial. Okay. All right. So yeah. So back to here, it says in another way, because the degree of f of x is n, because of this, we know an is not 0, right? And similarly, we know bm is not 0. So when we multiply the two together, we'll have an xn will at least have this term plus bm, not plus, multiply bm xm gives you an bm xm plus n. Okay, and because neither of these are 0, so therefore an multiplied by bm is not 0. So the degree of h of x therefore is m plus n. Okay, so the other way of saying is degree of h, equals degree of f plus degree of g. Okay, so this is similar like the exponent calculation. When you multiply the two, you actually just adding the exponents. You multiply, say, I think we learned before 2 squared multiplied by 2 cubed, you end up with 2/5, right? You do this, your multiplication, you actually reduce the complexity of calculation by adding the exponents together. Okay, so same over here, you're multiplying the two, where h equals to f multiplied by g. When you multiply the two together, the degree you add together. It's very similar to what we learned at the very beginning of this book of exponent calculation. Kevin, I know that exponent calculation is kind of confusing to you, which next week or maybe today we'll touch on the exponent again. Hopefully that will be helpful to clarify things for you. But I just want to emphasize again, we start with addition. When you're in first grade, you add things together, and then you learn to multiply, right? When you add the same number multiple times, you can simplify. So we have a plus a plus a. You can do that 3a, right? And then we have multiplied, we have repetitive pattern. We have a multiplied by a multiplied by a. We have come from multiplication. We can go to exponentiation, right? Exponent. So this becomes a cubed. These are all kind of you can say it's simplifying notation, but it's just a generalized calculation. We don't have this going higher power. Well, I guess we could. We have a cube squared, right? And then this just becomes a3 multiplied by 2, right? It becomes all kind of a converge to the exponent calculation. These are, I would say, it kind of limits us to the dimension we have. So these are These are all related to each other. Anyhow, so that's the first part, right? So the degree of the product polynomial is the degree of the two polynomial added together. That gives you the highest term. Okay, let's see what is the, okay. Part B is if f of x or g of x are monic, meaning their leading terms has coefficient of 1, must h of x be monic as well? No, it's actually yeah, sorry. Yes, it has to be. So when it's monic, that means the highest term. So an equals to 1, bm equals to 1. Therefore, an multiplied by bm is also 1 multiplied by 1 equals to 1. So yeah, so what it means monic is the leading coefficient equals to 1. So therefore, you would have the g of x, or sorry, h of x as the product of the two will also have a leading coefficient of 1. So they're also monic. Okay, even if h of x is monic, so on the other hand, if h of x is monic, must f of gx also be monic as well? That's not true, right? So we can draw this conclusion. However, if an multiplied by bm equals to 1, it doesn't mean an equals to 1 and bm equals to 1. It just means bm equals to bm equals to 1 over an. We know an is not 0. As long as bm equals to an multiplied by 1 over an will always be 1. And that doesn't, except the special case when an equals to 1, it doesn't make this f and g monic, right? Makes sense? So they can cancel each other out, so it's not monic. Okay, so sorry, go back here. If the constant term of f of x is 0, must the constant term of g of x also be 0? Okay, if the constant term of g of x, h of x is 0, is it possible for both are non-zero? Okay, so that we're basically we're studying the properties of the product, right? We know the constant term of h of x will equals to a0 multiplied by b0. Why is that? Because every other term will have x in it. These are the only two terms that doesn't have an x in it. Going back here, you see this is the two constant term. There's only one, right? As you multiply like this, there's only one that gives you the constant term, just like there's only one that gives you the highest leading term. All the others have multiple ones you can simplify together. You can actually if it's in the order, you can actually count how many. So you have 1, 2, 3, and 3, 2, 1. It's actually symmetric, right? If you have another term, you have 1, 2, 3, 4, 4, 3, 2, 1, right? So the leading term and the constant term are the only terms that are unique, meaning there's only one combination that gives you that term. So the constant term is a0 multiplied by b0. So let's see what our question is. The constant term of f of x is 0. So that means a0 equals to 0. Then for h of this is not equal. This comma, the constant term of this a0 b0 is also 0. Okay, if one of them doesn't have a constant term, the whole product has no constant term. Okay. If the constant term of h of x, if a0 multiplied by b0 equals to 0, is it possible that a0 is not 0 and b0 is not 0? We know the product is 0 only if one of them is 0. one or both of them are 0, right? So it's impossible for the constant to all be non-zero. If you have two non-zero terms, you always have a non-zero term, like constant term for the product. If one of them or both of them are 0, then you have the 0 constant. Okay. So here's the conclusion. If f of x and are non-zero polynomials, okay, then we have the following conclusion. The degree of f multiplied by g is the sum of the two degrees, the two functions' degrees. The product of the leading term of f of x and g of x is the leading term of the product of f of x, g of x. The product of the constant terms of g of x and f of x are constant term of the product of f of x, g of x. This is what I showed you earlier. The highest term goes with the highest term and the lowest term, or the constant term goes with the constant term. Okay, the two ends are unique. You only have one combination, so there's no way for you to cancel anything out. But the middle terms, you have at least two to combine, and therefore you can have other situations. Okay, we learned about the product of two polynomials without actually multiplying any polynomials, right? Let's try this. Okay, these are just like properties you study, so you can actually get a sense of things without actually doing it. And that also is how you can check your answers when you actually do something. So with this, we do a practice. So x3 plus bx squared minus 7x plus 9. Now we're talking about the middle terms. X squared plus ax plus 5, not b. Okay, and we know this equals to x5 plus 13x4 plus 38x cubed minus 22x squared plus 37x plus 45. Okay, we know this. So we're asked to find A and B. Okay. All right, so we talked about the highest term, and we can check over here the highest term, the harmonic. So x cubed, x squared gives you x4 fifths. So that's checked off. The constant term, 5 and 9. And 5 and 9 gives you 45. Okay. We have the fourth term, third power, second power, and first power. Okay. All right, we could. So in order to find A and B, A is this term, right? Sorry, B is this term, A is this term. In order to find A and B, we can just find the corresponding term that gives you these terms. Right. We can multiply everything out and then match the power and find out which term goes with which. Or we can be a little bit smarter without expanding everything, right? So the slow way of doing it is expanding the entire thing and match terms. But we are actually a little bit, can be a little bit more smart on that. So let's see how we're gonna do this. We're just gonna do a portion of the expansion, right? So let me go back here again. Right, so from this one, we know the first one is like, 4 terms. The second one is 3 terms, right? Just similar to this one, 4 terms and 3 terms. And we know that we can potentially have 4 because this B is over here, this A is over here, right? So we can potentially have 4 different linear expressions to solve for A and B. Makes sense? Because each one gives you a equation. We, however, probably only need 2. If we only need 2, we're gonna find the simple one. We're gonna find the one that has 2 terms, right? So these two terms, rather than the 3-term ones. Make sense? If you are smart, you're gonna use this knowledge, we're going to look for the simplest one. We're going to look for the first power and the fourth power. We can use the third and the second. You know, just because we can, it doesn't make our life easier. We always go with a simple solution. If we can't solve it using these two, then we go here. Make sense? So even before you start, you know, think of it and then try to make it make life easier for yourself. Okay. So go back here. Let's see. We know this one. So 37x must be from this two and this two. Make sense? That's the only two terms that gives you the first power. So we have 9ax. Oh, be careful about the signs. Minus 35x. Okay, so this gives me 9ax equals to 72x. Yeah, and that tells me a equals to 8. Okay. All right, so then we go the next one. We go the fourth power. So we have 13x fourth, not 13x fourth. X fourth are this two. This gives me x fourth, and this gives me x fourth. Right. So we have ax fourth plus bx fourth equals to 13. I already know a is 8, so I have 8 x fourth plus b x fourth equals to 13. Therefore, that tells me b equals to 5. Okay. So therefore, we have, x cubed plus 5x squared plus 5x squared minus 7x plus 9 and x squared plus 8x plus 5. You see? Make sense? Okay. We can actually multiply this out to confirm that our answers are correct, but you know, that's a lot of work. Okay. You could also test and see if we use the x cubed and x squared terms. In that case, we have this one and this one, this one and this one, this one and this one gives you x cubed, and the other combination that gives you x squared. It will end up the same, give you the same answer, but this is two terms and it's easier to solve. Okay. So if f of g are polynomials such that h of x equals to f of g, f of x multiplied g of x, then each term is a result of a combination of appropriate products of a term of f of x and a term of g of x. Using this fact can simplify problem solving, the product of polynomials. Right. So this this avoids you have to go through all the gory, like expanding the whole product. So that's the end of chapter 18. It's a short chapter. So we have about 10 minutes left. And I didn't know when Gordon dropped. Okay, so Anders, you're sure about no tennis now? Okay, all right, so what I want to do is use this time to kind of talk about the beginning of the next chapter, and we'll get into exponents and logarithm next week. And the reason is, I think chapter 19 is a bit long, so hopefully, I don't know if I'll be able to finish in 1 week, so we'll get started on this, okay? So exponents, oops. You know what, I'm gonna I'm gonna go back home. I'm gonna start a new whiteboard on chapter 19. There we go. So let's see, chapter 19. We have exponents and logarithm. This is like a very high level introduction of the topic. Although this part seems really complex, it's not actually not hard. It's a very simple introduction. There's more you can get into it, but I think this should be good for our discussion. So let's start with a simple example, just some terminology, right? So this is something we are familiar with. 2 to the cube gives you 8, which equals to 2 times 2, 2 times 2, 3 times. 3 times is represented over here, means 2 multiplied by 2, 3 times. Okay, that is 8. And this 2 we call base, the base number, okay, 底数. This 3 we call exponent, 指数. Okay, so these are exponent and base. That's all you need to know. Okay, so we usually know that this is the we usually okay, we usually see function in which a variable is raised to the various. So like say what we have earlier is x to the nth power, right? The variable, even though they're all letters, this is a variable, and is usually denoted as a constant, so, right? So x, y, z. So this one is a variable is x, or we can say x cubed. Then we know x is something we don't know. The base is something we don't know. However, it's also possible that we have a function that's n to the x power, right? So the base is known. However, the exponent is the unknown. Okay, we studied really thoroughly, like when the variable is here, we have the power and we know which degree it is. And now we're on the switch our focus on what if the exponent is the unknown value? You know, how do we solve this problem, right? This, so f of x equals to, actually we usually say b to the x, base to the x power. This is an exponent function. Okay, so here's a story which I think you can read on your own. It's like basically asking for rewards, and the whole point is the exponential explosion of growth, which actually in early days of COVID, that's the biggest debate is, you know, things may seems to be small, but because it's exponentially growing, so it's very likely to expand into a pandemic. And that's where a lot of people were debating is whether it's a polynomial growth or exponential growth, but I'm not gonna get into that right now. So we'll just focus on a couple of problems. We have about 8 minutes. I think I should be able to cover 1 or 2 problems. But in this problem, we build functions to declare how much, oh, I guess we still need to talk about the story. So high level, the story goes like this, right? So we have 2 people. They all did something good, and the king wanted to reward them. And the king asked, how do you want to be rewarded? And a chessboard, you know a chessboard. So Ariel asked to have 1 grain of the rice placed in the first square of her chessboard, and she asked to each day thereafter the king place amount of the rice on the next chessboard that was 10 more than grains on the amount of the rice in the previous square. So 10 more, right? So you know each subsequent ones becomes 10 more. Okay. And then Mina say, okay, I don't want to have 10 more. I just want to have the chessboard to double, I want to have the next one to double the amount of the day before. And the king agreed. It's not like, you know, he's like, oh, 10 times, that's 10 more, that's a lot more. And double isn't 1 to 2, 2 to 4 isn't that great, isn't that large of a number, right? So for example, they all start at 1, and then you have 1 to 11, and then 21, and then 2 to 1 to 2, 2 to 4, right? So the question is which person gets a better deal? At first, from these two numbers, it seems like the area gets a better deal, but let's set up the problem, right? So in this problem, we build to describe on the nth day, right? So an, okay, areas. So the first day is 1, and the nth day is 10 times n, right? Well, actually 10 times n minus 1, because the second day is, the first day is 1. The second day is only when n started. So this equals to 10n minus 9, okay? So the first day when n equals to 1, a1 equals to 1, a2 equals to 11, a3 equals to 21. It seems to work out, right? Okay, so Mina, mn equals to 2 to the nth power minus 1, I think, right? Because it starts with 1. So we say n1 equals to 2 to the 0 is 1, and m2 equals to 2. You double 1, you get 2, and 3 equals to 4. Okay, so that seems to work out. So this is our function, right? We figure out, we're trying to figure out who gets a better deal, right? So now we have the two functions. So a n equals to 10n minus 9, m n equals to 2 to the n minus 1's power. Okay, so by day 7, so a7 equals to 61, 70 minus 9, m7 equals to 2 to the 6th power, which is 64. At the 7th day, m already overtook a, right? It's already more than a. Before that, m is less than a, okay? By the 21st day, well, I guess we go by multiples of 7. So a14 is 138, 31. M14, I'm not going to calculate it out. Well, this one is easy, 140 minus 9. This one is 2 to the 13th power. I'm not going to calculate it out. It's already 8,092. Okay, so it's already significantly higher than this number. Okay, so by the day, the 21st day, it's already millions of grain. Okay, so definitely the answer is that Mina is getting a better deal out of this. Okay, so this is what we called about exponential growth. Okay, this is what happens to exponential function is it grow really, really fast. Okay. I don't know how many squares are on the chessboard. You can actually figure out on the last day. On the last day, Mina probably can bankrupt the king because the number is so large. So anyway, so I kind of went over that problem pretty quickly. Are we good? Make sense? Thumbs up. Thank you, Yo-Yo. Okay. All right, so I think we have time to do another problem. Graph the function of f of x to the x power, f of x equals to 2x. By the way, I want to point out this is not a polynomial. This is an exponential function. Okay, determine its range. So I'm not gonna graph it out, but you can see over here, okay? The range, the domain is actually the entire, so X can be any number on the number line, right? The smaller it goes, the closer the number is to 0, but it's never touching 0, okay? However, the larger it is, it's really, really high. It grows really fast. So the shape of the function is very, very close to 0, okay? And here it's 1, 1. When X equals to 0, it's 1, and then it goes this way. It's called exponential growth, this explosion, right? It climbs really, really quickly. This explosion is the characteristic of an exponential function when a is greater than 1. Okay, so when x is 0, it's always 1. Depend on the base. When it's 1, it always is the base. So in this case, this is 1 and this is 2, right? So these 2 points are always sort of fixed or null. So if you have g of x equals to 3x, then this point is over here, and g of x at 1 will be this point, and it will grow even faster. This will degenerate even faster, but will all get very close to 0. So it's a characteristic when a is greater than 1, then such function sometimes an exponential function, and graph for value of a where a is greater than 1. So we always say a is greater than 1 because when a is less than 1, okay, so let's just study when a is 1, what does the shape look like? When a is 1, it's always 1, right? It doesn't matter what this is 1 to the x power. It doesn't matter how many, what the value of x is, you always end up with 1, right? This, when a is greater than 1, you grow. When a is less than 1, you actually go the other direction. Okay? They're symmetric. So this is when a is less than 1. Okay, so for example, this is 2, then this is 1 over 2. Why? Because 1 over 2 is 2 to the negative 1. You basically just switch the sign of x, and they're like actually mirror image of each other, just on the different sides of the graph. So because of that, a equals to 1 is a trivial case. We don't need to study. A less than 1 is just the symmetric mirror image of a greater than 1. So we only study ax when a is greater than 1. F of x equals to ax. Make sense? I think I'm running out of time this week. We'll come back and pick up from 9.3 next week. Sounds good? Okay, and it's also asking the range. The range is everything greater than 0. The domain is all entire real number here. Okay. All right, I'll see you next week. Sounds good? Have a good week. Bye.
Bye.